Around 444 million years ago, the world's oceans suffered a massive die-off. Not a total wipeout, to be sure. Life's stubborn persistence often finds a way, hunkering down in overlooked spots where the environment stays just survivable enough. But imagine yourself along the coastline of that primordial Earth, gazing as waves lapped over the continental shelves. You'd sense an eerie disturbance right away. The liquid at your toes would appear far more transparent than any modern sea. And that transparency revealed the grim truth. Pristine waters signify barren ones. Gone were the myriad microscopic creatures that typically murk up the depths with their forms, their excretions, and their perpetual chain of predation and consumption. The entire ecosystem had unraveled. This marked the fallout from the Ordovician Silurian extinction, Earth's second worst disaster for multicellular organisms. Fully 85% of marine species vanished in what geologists call a mere blink, an event spanning two deadly waves roughly 1 million years apart. A trivial interval in the grand sweep of geological time. The initial surge arrived amid freezing conditions. Enormous ice sheets engulfed the southern supercontinent Gondwana, sequestering vast quantities of water and causing sea levels to crash dramatically. The coastal habitats, home to most thriving species, simply vanished beneath the exposure. Animals shaped by eons of evolution suddenly faced a landscape with no space left for them. The follow-up wave brought heat instead. With the ice melting and oceans rebounding in level, one might assume relief for the biosphere. But the rising temperatures unleashed a darker threat. Surface layers warmed and layered over cooler, oxygen-starved depths, creating barriers in the water column. Huge swaths of the ocean bottom went fully anoxic, stripped of the oxygen essential for advanced life. In certain zones, conditions tipped into euxinia, where hydrogen sulfide, the foul gas behind rotten egg odors, built up to lethal levels. The oceans had become toxic traps. The toll spanned the spectrum of marine biodiversity. Trilobites, those tough-shelled arthropods that had ruled the seabeds for more than 100 million years, watched whole lineages perish across mere thousands of generations. Brachiopods, the bivalve-like clams that once blanketed shelves in unimaginable profusion, endured a sharp drop in variety. Bryozoans, graptolites, corals, crinoids, each prominent clade, endured the reaper's cut. Reef ecosystems, painstakingly constructed since Cambrian times to foster intricate biodiversity, lay in ruins as their architect species perished. Remarkably, though, once the onslaught eased and ocean chemistry steadied, the holdouts didn't just huddle in reduced populations, biding their time. They surged forward without delay. The voids carved by the lost species resembled deserted buildings in a post-plague metropolis, and the hardy remnants quickly claimed those untapped roles. Brachiopod genera, previously restricted to Laurentia's fringes, fanned out worldwide in under a few million years. Scant surviving corals started branching into new forms, their offspring seeding reef frameworks to match or exceed Ordovician splendor. This era of rebound and reinvention earned the name Silurian, honoring an old Celtic group from the Welsh border region, where such ancient strata first drew scrutiny. Spanning about 24 million years, a fleeting span in Earth's epic timeline, it amounted to just one vivid section in the planet's vast chronicle. Yet what a pivotal one. In the waters, fishes gained jaws for the first time, a seemingly simple shift that underpins every vertebrate bite since, right up to your own. Enormous arthropods, known as eurypterids, stretch to 2.5 meters, evolving into the biggest of their kind ever to exist. Top hunters in a realm still mending from ruin. Meanwhile, ashore, a profound shift was underway. For nearly 4 billion years, the land masses had lain desolate, bare stone, dunes, and quiet beneath a UV-bombarded sky lacking any ozone shield. But the Silurian air transformed, with oxygen climbing and paving the way for an ozone layer to enable land-dwelling organisms. Minute vascular plants, scarcely finger-high, started claiming stream banks and tidal zones. Their plumbing-like tissues heralded a botanical breakthrough, destined to cloak the globe in verdure. Trailing them arrived arthropods, millipedes, centipedes, and early spiders, the inaugural air-breathers and true terrestrials free from watery retreats. We'll trace these tales in the time to come. The emergence of reefs, the colossal creatures of prehistoric oceans, the dawn of jaws, the spread of greenery over land. If this adventure piques your interest, please get comfortable and join us for the ride. There's a special serenity in surrendering to the vast expanse of geological time, in tracing the gradual pulses of evolution over eons. Think of this as your welcome to unwind, to tune in, and to allow the echoes of antiquity to transport you to any solace you seek this evening. The balmy oceans of the early Silurian extended over continental platforms vastly wider and more shallow than those we know today. Elevated sea levels, driven by the thaw of ancient ice sheets, had surged upward, inundating the flat heartlands of land masses and forming expansive inland seas that reached deep into territories spanning hundreds of kilometers. Within these sun-drenched temperate waters, the stage was set for life to rebound vigorously. Rays of light penetrated to the seafloor, sparking photosynthetic activity. Essential nutrients circulated throughout the depths, bolstering the foundations of emerging ecosystems. And in this nurturing habitat, the resilient remnants proliferated across successive generations and lineages, repopulating the void with vitality, vibrancy, and the ceaseless pulse of existence. Yet to grasp the full essence of the Silurian era, we first need to examine the backdrop of this epic tale. The land masses of that distant planet shared little with the outlines etched on our current atlases. They floated in strange arrangements worldwide, divided by vanished seas and inching toward impacts that forged enduring mountain chains we still see. During one such convergence, fragments of crust parted for hundreds of millions of years at last converged. In that union, the terrain now called Scotland fused with England for the initial time, although those labels wouldn't appear for 400 million more years. The narrative of the Silurian is etched in rock layers preserved in fossils and revealed through the molecular signatures of enduring strata, exposed in places like Wales, Sweden, and the Midwest United States. It's a chronicle of devastation and renewal, of a planet rising from ruin, not just renewed but profoundly reshaped. In the sections ahead, we'll chart that saga from the barren waters, left in the wake of mass, dying to the initial ventures onto terra firma. From the plated swimmers patrolling primordial depths to the enormous hunters that stalked them, from the crashing of plates to the subtle shifts that would one day sprout every woodland and field in our world. This is the Silurian as science reconstructs it. Recovery kicked off in the coastal shallows fringing Laurentia, amid mild waves washing the site of present-day eastern North America. Signs of revival appeared mere hundreds of thousands of years after the apocalypse concluded. To our minds, shaped by views of evolution as a glacial crawl spanning incomprehensible epochs, this pace feels astonishingly swift. But the holdouts possessed an unprecedented advantage: unoccupied territory. Ecological slots lay open. Rivals had perished. The hunters that once curbed growth for ages were gone, and the persisting life forms confronted a realm where proliferation faced no barriers beyond reproductive speed. Around Laurentia, species richness rebounded to pre-catastrophe heights in about 5 million years. By our fleeting human measure, that's an eternity. Long enough to rewind from now to the era when early human forebears first strode erect across African plains. Yet on geology's grand ledger, 5 million years is a mere blip, scarce duration for loose particles to compress into distinct strata. On a worldwide scale, full restoration stretched further, maybe 15 million years, until global marine diversity matched its pre-crisis peak. Certain zones suffered more severe blows, leaving their remnants with steeper paths to revival. Reweaving elaborate trophic chains demanded far more than populating gaps with any viable occupants. The delicate interlinks among organisms, from hunters to hunted to the tiny decomposers handling remains, had to reform via endless cycles of experimentation across progeny. Still, the most profound shift lay not in recovery's velocity, but its essence. The Ordovician realm had featured a mosaic of isolated bioregions. Every landmass sheltered its singular suite of life forms, honed separately over tens of millions of years. A brachiopod on the bottom near modern Morocco would have borne scant similarity to relatives off Laurentia. The die-off upended that pattern. With 85% of lineages erased, the remnants weren't a haphazard cross-section of prior abundance. Survivors of such events often proved to be adaptable generalists, creatures with wide-ranging tolerances and versatile ways of life that helped them outlast their more narrowly adapted counterparts amid the chaos. Once the upheaval subsided, these resilient types proliferated swiftly over the revitalizing planet. Their offspring ventured into habitats stretching from equatorial zones to polar extremes. The regionally unique fauna of the Ordovician yielded to a much more widespread assembly, as though evolution had reset the board and begun anew with a more uniform set of biological tools. This shift stands out vividly among the brachiopods, the bivalved invertebrates that mimic clams in appearance yet occupy a wholly separate lineage on the tree of life. Prior to the mass die-off, brachiopod assemblages differed sharply between locales molded by eons of site-specific evolution. In its wake, just a few enduring groups dispersed globally at an astonishing pace. The pentamerids, for instance, exploded in diversity during the early Silurian. Thick-shelled offshoots of theirs cropped up in comparable settings across virtually all landmasses, though with a notable caveat. These fresh pentamerids tended to be markedly smaller than their Ordovician forebears, a recurring trend dubbed the Lilliputian effect, which surfaces repeatedly in the recovery phases following major extinctions. In eras of instability and limited resources, natural selection prioritizes compactness, rapid development, and efficiency. The brachiopods were essentially re-establishing their prominence, yet they weren't operating in isolation. Along the expansive continental shelves, additional holdouts set about crafting something grander: the foundational framework of ocean ecosystems. During the Ordovician, reef networks had achieved remarkable intricacy, with corals, sponges, bryozoans, and numerous other builders forming elaborate, multi-dimensional refugees for myriad tiny dwellers. The catastrophe had shattered these biogenic edifices, reducing vibrant realms to barren debris zones. But in the gradually warming Silurian oceans, fresh architects started erecting bases that would ultimately eclipse the Ordovician's grandest achievements. Stromatoporoids spearheaded the revival. These calcifying sponges had scraped through the extinction in reduced populations. Yet the vacated shelves provided ample space for growth. They stacked up in tiers with successive layers encrusting the mineralized skeletons of predecessors, forming rounded domes and ramifying forms that, over millennia, swelled into hill-sized mounds. Working beside them, tabulate corals, colonial polyps that secreted intricate, honeycomb-patterned calcium carbonate frameworks, began taking root in the shallow, light-filled waters. Should you have explored those nascent Silurian reefs, they'd have seemed humble beside the behemoths to follow. But they were paving the way for sprawling reef complexes that would soon line continental edges for hundreds of kilometers. Certain other remnants fulfilled subtler yet crucial functions in restoring marine life. Crinoids, the elegant suspension feeders often likened to sea lilies for their floral looks, fared relatively well through the crisis, with about 70% of their genera enduring. Throughout the Silurian, they blanketed shelves worldwide. Their delicate arms swayed with the tides, snaring minuscule food bits and redistributing nutrients up and down the water layers. Graptolites kept drifting toward their Ordovician peak's gradual fade-out. Even so, these clustered drifters stayed vital in the floating plankton ranks, and their signature blade-shaped fossils later became key for paleontologists, correlating Silurian strata across vast timescales. Then came the trilobites, the plated arthropods whose traces mark more than 300 million years of terrestrial drama. The event struck them severely, wiping out whole clans and slashing their former profusion to a shadow. Full rebound eluded them forever. Silurian trilobites were remnants of a fading empire, clinging on as the world edged onward without them. Still, strolling the seafloors of Silurian Laurentia, you'd have encountered them in abundance, crawling over the muck with multifaceted eyes alert to prey and threats. Calamen, noted for its coiled-up protective stance, grew so prevalent in what is now Wisconsin that it earned designation as the state's fossil, a nod to the warm, shallow seas that, long ago, inundated the Midwest. Such recovery motifs, adaptable types supplanting specialists, global wanderers ousting local endemics, diminutive forms succeeding giants, echo in the wake of every grand extinction our planet has endured. It appears life carries a reliable manual for resurgence from calamity, a repertoire of tactics effective no matter if the trigger was ice sheets, eruptions, or cosmic impacts. The Silurian rebound transcended simple echoes of past recoveries. As surviving species claimed the voids abandoned by the fallen, an extraordinary shift was unfolding in the abyssal realms of this end times landscape. Within the branchial arches of select fish, cartilaginous tissues curved into innovative forms, presaging the rise of jaw-like apparatuses. Over the stark land expanses, where intense UV exposure kept the terrain lethal for intricate organisms, oxygen levels in the air crept upward steadily, inching toward a critical level poised to reshape the globe. Meanwhile, along the near-shore shallows, minuscule life forms ventured into bold innovation, existence beyond oceanic confines. The post-extinction resurgence morphed into something profoundly different, a seismic transformation. Any contemporary viewer would deem the Silurian continents wholly unfamiliar. Peering at Earth from orbit 430 million years in the past, one would scan futilely for the contours of Africa, the Americas, or Eurasia's broad sweep. The scene instead unveiled a water-blanketed sphere, dotted with continental blocks arrayed globally in patterns defying today's charts. The southern realm hosted a colossal supercontinent known as Gondwana, melding lands fated to fragment into Africa, South America, Antarctica, Australia, India, and slivers of southern Europe. This seamless expanse arced from the South Pole beyond the equator, dwarfing all present-day continents in scale. Gondwana shared that primordial domain with others. Straddling the equatorial belt, amid balmy climes, stood Laurentia, a land incorporating much of today's North America, Greenland, and a segment of modern Scotland. Stones destined for the Scottish Highlands lay isolated from England's bedrock by thousands of kilometers of vast seas, a revelation that catches many off guard, given assumptions of Great Britain's eternal wholeness as a geological entity. Laurentia's equatorial perch enveloped its broad shelves in sun-drenched, temperate seas, nurturing prime habitats for reef ecosystems regenerating in extinction's wake. Eastward from Laurentia, beyond a constricting arm of sea termed the Iapetus Ocean, a rival continent inched nearer. Baltica encompassed the bulk of Scandinavia, the Baltic nations, and swaths of Eastern Europe. Across the Silurian, it wheeled and migrated toward a fated merger with its heftier counterpart. Nestled amid them, reminiscent of a modest craft trapped by looming vessels, floated Avalonia, a lithe microcontinent that had calved from Gondwana scores of millions of years prior and now veered poleward. Avalonia transported the lithic precursors to England, Wales, southeast Ireland, and eastern Newfoundland's edges, discrete crustal puzzle pieces, slated for attachment to grander wholes as the gaps between dissolved. The Iapetus Ocean faded into obsolescence. For eons spanning hundreds of millions of years, it cleaved Laurentia from Baltica, a Atlantic-scale expanse, nurturing unique aquatic biotas and circulatory regimes all its own. Yet the engines of plate motion herded these cratons inward at several centimeters yearly, modest in mortal reckonings, inexorable on deep-time scales. Come the late Silurian, the Iapetus had slimmed to but a remnant of its prior girth, its total obliteration via collision already afoot. Such a clash forged towering ranges, with Baltica and Avalonia bearing down on Laurentia. The lithosphere wrinkled and warped, thrusting strata skyward into summits conceivably matching the Himalayas' stature. This orogenic surge, dubbed the Caledonian orogeny by Earth scientists, endures in traces across Scotland's uplands, Scandinavia's peaks, Wales's undulations, and the Appalachian's northern flanks. Traversing the Scottish Highlands places you atop the weathered stubs of elevations thrust up by continental crushes exceeding 400 million years ago, timeless relics of a bygone realm. The juncture likewise conjoined terrains that had matured in isolation for hundreds of millions of years. Laurentia-born Scotland at length encountered Avalonia-conveyed England adrift northward. Their weld line, the Iapetus suture, shadows the contemporary Scotland-England divide, veering through Ireland besides. distinct crustal sagas bearing disparate fossil suites. These realms amalgamated into the bedrock of a forthcoming unified landmass. If anyone claims that Scotland and England have shared a single nation since the beginning, remind them that for the vast majority of our planet's past, those regions sat on opposing shores of a wide sea. As landmasses crashed into one another in certain areas, others stayed fragmented and adrift. In the north, Siberia wandered independently, isolated from the primary continental chunks by enormous expanses of the Panthalic Ocean. Meanwhile, the South China and North China cratons functioned as isolated pieces, unconnected to one another or any other land. Such detached land blocks fostered unique ocean communities. Yet the widespread character of Silurian organisms ensured that comparable creatures thrived in matching habitats no matter the underlying shelf. The worldwide layout during the Silurian deeply influenced sea flows, weather patterns, and the spread of organisms. Since land clustered heavily in the south, the North's polar zone featured mostly unobstructed waters. The immense Panthalassic Sea, which spanned almost half the globe, enabled equatorial heat to travel smoothly across the world, spreading warmth and stabilizing climates. Consequently, the era's temperatures averaged higher than ours, with warm, shallow waters inundating the lower parts of continents and forming huge zones for sea creatures. Known as epicontinental seas, these inland floods had no equivalent in today's landscape. Picture the full Mississippi Valley immersed in mild, shallow salt water, extending from the Gulf of Mexico up to Hudson Bay. That's akin to what blanketed much of Laurentia in the Silurian. At peak flooding, about 65% of modern North America submerged under the sea. Depths stayed modest, seldom exceeding a couple hundred meters, letting sunlight reach the seabed over broad swaths. Such settings ideal for piling up carbonate layers, fostering reef ecosystems, and sparking bursts of sea life variety. Toward the Silurian's close, these inland waters started pulling back. Falling sea levels uncovered terrains hidden underwater for eons. In the resulting depressions, drying intensified the leftover brine into salty lagoons, which later formed dense layers of salt and gypsum. Evaporate deposits that persist beneath swaths of the U.S. Midwest, from Michigan through West Virginia. This withdrawal signaled a shift to a transformed landscape. Soon, the emerging supercontinent Laurasia would command the north, priming the scene for life's upcoming major saga. Yet that change lay millions of years off. In the balmy, inundated realm of the early to mid-Silurian, circumstances primed one of the grandest advances in ocean biology. The emergence of the planet's premier extensive reef networks, organic edifices that outshone prior efforts and wouldn't be matched again until today's coral era. These seafloor formations were unprecedented. For eons, only bacterial films and stromatolites had managed to erect from the depths, their stacked mounds topping out at just a meter or so high. The Ordovician brought initial animal-crafted reefs, simple setups from bryozoans and primitive corals that previewed the potential of cooperative habitat building. But the mass die-off had demolished most of those trailblazers, scattering debris and voids. Now, amid the Silurian's temperate shallows, fresh constructors prepared to erect far grander works. Vast reef arrays would line continental edges for hundreds of kilometers, towering dozens of meters high and offering intricate refuges for thousands of species. Leading this sub-sea build-in surge were stromatoporoids, enigmatic calcareous sponges without modern kin. Their inner workings, still somewhat obscure. They expanded by depositing calcium carbonate in successive layers, each layer atop the prior one's hardened frame, amassing over millennia. Certain types spread as encrusting pavements along the bottom. Others swelled into broad domes spanning meters wide. Some shot up in branchy forms like petrified trees, their honeycombed frames laced with passages for water flow through the active flesh. Touching a live stromatoporoid might resemble handling damp cement, firm yet textured, pocked with minuscule openings everywhere for pulling in water to sift out tiny food bits. These ancient sponges weren't the only architects at work. Teaming up with them, either sprouting right on their exteriors or squeezing into the spaces amid their enormous bodies, came the tabulate corals. These group-living creatures formed intricate, honeycomb-style frameworks from calcium carbonate. Every single polyp resided in its dedicated narrow tube, all pitching in to expand the colony's framework. One frequent sight was favorites, often dubbed honeycomb coral for its clear resemblance, with its fossil remnants easily spotted thanks to the orderly hexagonal arrangement of those tubes. Halides, known as the chain coral, formed unique interconnected rings that resembled strands of rocky beads strung over the reef's face. Helolids chipped in too, their colonies dotted with minuscule star-like apertures where polyps once stretched out tentacles to snag drifting morsels. In unison, the stromatoporoids and tabulate corals forged a true innovation in life's timeline. Sturdy carbonate platforms that could endure the relentless pounding from sea swells and tempests. Prior reefs were delicate setups, quick to shatter under fierce waves or moving sands. But Silurian reefs stood apart. The hefty bases from the stromatoporoids offered solid footing, as the corals sealed voids and boosted the framework's intricacy. One stratum after another piled up, season by season, era upon era, until certain formations towered over 100 meters high from the nearby ocean bottom. Submerged peaks crafted solely by biological forces. Such reefs weren't standalone features. They functioned as full-blown habitats, intricate networks hosting scores of species that sourced nourishment, refuge, and breeding grounds. Crinoids latched onto firm spots and unfurled their delicate, feather-like appendages into the flow, sifting out minuscule bits from the seawater. Brachiopods huddled in protected nooks, their bivalves parting just enough to pull in the food-laden currents weaving through the reef's architecture. Bryozoans coated any open area, these diminutive colony dwellers lending their bit to the expanding calcium carbonate bulk. Trilobites roamed the edges, picking over decayed organics and pursuing tinier quarry. Snails nibbled at algal growths. Cephalopods, forerunners of today's squids and octopuses, yet still sheathed in outer shells, patrolled the waters overhead, near the reef's top. The real wonder of these assemblages lay in their biological depth. Today's coral systems earn acclaim for their species' richness. The tangled chains of hunters and hunted, the myriad tailored roles occupied by creatures fine-tuned for precise lifestyles. For the first time on our planet, Silurian reefs neared that sophistication. Life forms weren't just coexisting nearby. They engaged in advanced interactions, crafting alliances that aided everyone involved or clashing in perpetual cycles of adaptive rivalry. Certain tabulate corals thrived solely inside stromatoporoid tissues, a mutual bond whose precise dynamics remain a puzzle for experts. Did the corals thrive on the reliable base and shielding from the sponge? Might the sponge have reaped advantages from sheltering the coral? The stone records capture the partnership, but leave the motivations unclear. Fresh studies indicate that a few of these old reef shapers might have mirrored a key trait of present-day corals: photosymbiosis. Examining oxygen isotopes in Silurian coral frames points to some kinds possibly harboring light-making algae in their bodies, much like today's reef formers. Should this hold, it would shift the dawn of that coral-algae partnership, back by hundreds of millions of years from earlier estimates, while shedding light on how Silurian reefs managed such rapid expansion in the low-nutrient seas along warm continental margins. Traces of these primordial reef networks persist for exploration now, albeit reshaped nearly past identification after 400 million years of earthly upheavals. The Swedish island of Gotland, situated offshore, holds some of the planet's premier Silurian reef outcrops. Strolling its rugged shores, you're treading the squeezed and hardened echoes of vibrant reef societies that flourished when this slice of Baltica basked in equatorial tropics. The stromatoporoids now form drab limestone, their stacked patterns detectable with a trained eye. Corals show up as motifs in the stone, honeycomb grids and chain-like circles etched forever. At spots, the reef's initial 3D form endures, with vast hillocks protruding from adjacent layers, mirroring how they once jutted from the prehistoric seabed. Comparable formations of these reefs can be found throughout the Midwest United States, spanning Wisconsin, Illinois, and Indiana, where Silurian limestones create notable ridges and supply stone for numerous quarries. The reefs that originally bordered the tropical edges of Laurentia are now hidden under vast farmlands and residential areas. Their fossilized remnants sometimes surface in highway excavations and building projects. These prehistoric formations varied from modest patch reefs spanning only a few dozen meters to enormous barrier systems extending hundreds of kilometers along the continental edge. Certain ones towered up to 60 meters or higher. They were like submerged high-rises, constructed gradually by tiny organisms smaller than a fingernail. The Silurian reefs marked a dramatic advance in the intricacy of ocean life systems. Yet they weren't the sole transformation unfolding in those primordial waters. As stromatoporoids and corals erected their calcareous domains, a far more menacing presence lurked in the surrounding depths. Hunters unlike any that had previously roamed the seas. Heavily armored stalkers that attained sizes that continue to amaze researchers. Despite their long-standing label in scientific writings for more than 100 years, they weren't true scorpions. Eurypterids were part of the Helicarata group, the same branch that later gave rise to spiders, ticks, and horseshoe crabs. They respired via gills without lungs. Lacking a stinger or poison, they didn't fit any real scorpion criteria biologically. But when 19th-century naturalists first laid eyes on their fossils, the jointed torsos, the seizing limbs, the elongated tapered tails, they drew the boldest analogy at hand. Sea scorpions, the term endured, and it suits them well, for these beings were just as terrifying as their land-dwelling counterparts, only vastly bigger. The Silurian era was their heyday. Eurypterids had first emerged in the Ordovician, as unassuming forms that barely registered in the fossil archives. But the world after the mass extinction proved ideal for them. Maybe it was the recovering reef habitats brimming with prospective meals, or the lack of rivals that had previously limited their spread. For whatever cause, Eurypterids underwent a rapid evolutionary burst during the Silurian, occupying niches from seafloor foragers to top-tier hunters in open seas. More than 250 species arose over time, from ones fitting in a person's palm to behemoths surpassing an adult human's height. The supreme giant was Jacalopterus renni, a beast with a unique honor among all arthropods. It was the biggest ever to exist in its category. Full-bodied fossils are scarce, yet one preserved claw from Germany let experts gauge the overall dimensions of the monster it once armed. That claw spanned 46 centimeters, even without its end spike. The full limb would have extended further. By scaling up from comparable relatives, scientists determined Jacalopterus measured about 2.5 meters, around 8 feet, from snout to tail tip. With its huge claws thrust out, its wingspan topped 3 meters, broad enough to encircle a compact vehicle. Imagine this beast alive. Its form divided into segments like a lobster's, sheathed in a durable carapace that shone darkly and slickly in the low-light realms it patrolled. The front held 2 big compound eyes for spotting motion in turbid waters, plus a rear set of smaller, simple eyes, possibly for depth perception or brightness assessment. 6 sets of limbs projected below the torso, the foremost pair reshaped into those colossal grippers. The central one suited for locomotion or propulsion. The hindmost broadened into wide paddles that drove the animal forward at unexpected velocities. The tail concluded in a broad fin, acting as a steering fin, enabling Jacalopterus to navigate accurately while tracking quarry. What fueled it? Whatever it could seize. The Silurian and early Devonian oceans teemed with fish, some shielded by bone armor that appeared to offer solid defense against threats. Yet, Jacalopterus's pincers were designed to shatter. Their serrated inner surfaces could latch and pierce through even fortified targets. The fossil record reveals a brutal tale. Fish bearing claw-sized dents in their plating, scat with fishbone shards, trails indicating chases and takedowns of escaping victims. These weren't passive lurkers biding time for easy targets. They were dynamic pursuers gliding through the water layers, hunting actively, leveraging their immense bulk and armaments to rule any habitat they invaded. Among the giants, Jacalopterus stood out as the biggest, yet it wasn't alone in its massive scale. The pterygonids, a group of eurypterids that thrived during the late Silurian, included various species stretching beyond 2 meters long. Acutiramus, for instance, grew to around 2 meters and 10 centimeters, featuring extended claws ending in hooked spines that likely trapped victims with no way out. Pterygotus, the genus that named the family, attained lengths of 1 3/4 meters and spread over the narrowing Iapetus Ocean from North America to Europe, where its remains appear in the strata. These beasts acted like the great white sharks of their time, top-tier hunters ruling food chains that spanned vast stretches of continental shelves across thousands of kilometers. That said, not every eurypterid towered in size or terrorized as a predator. Plenty stayed modest, occupying roles as scavengers, drillers, or pursuers of minuscule invertebrates. Eurypterus remipes, arguably the most frequently preserved eurypterid ever, seldom surpass 30 centimeters, roughly the span of a hefty lobster. In some Silurian layers from New York State, its fossils pile up so densely that the state named it its official emblem. underscoring how those seas buzzed with shelled arthropods chasing their primordial pursuits. Certain eurypterids favored the ocean floor, scuttling along on numerous limbs, whereas others geared up for open water pursuits with fan-shaped tail fins and sleek forms optimized for velocity and agility. A fascinating element of eurypterid life involved their ties to terrestrial realms. Throughout much of their existence, they stayed wholly marine, as tied to water as fish. However, select branches evolved features suggesting brief land forays. Some bore branchial plate-like organs akin to book gills, potentially able to pull oxygen from both air and sea. Footprints etched in Silurian mudflats reveal eurypterids traversing those zones, their tapered limbs stamping patterns that hardened into enduring rock. We can't determine if these were everyday scavenging jaunts or frantic flights from threats or harsh seas, but the vision captivates. Plated behemoths, dragging onto beaches, maybe lounging on surf-swept boulders or stalking the initial arthropods venturing ashore. Imagine gliding through the near-shore waves of Silurian Laurentia. You'd encounter these beings amid the currents. The tinier ones could bolt at your presence, vanishing into cracks or digging into the muck. But the titans like Jacalopterus, Pterygotus, and Acutiramus shunned retreat from any foe. To them, you'd register merely as fresh prey, tender-fleshed and sluggish, without the plating or swiftness to dodge a clash. The Silurian oceans offered no haven. They formed prowling territories for hunters unmatched in the world's history. Still, even these plated colossi coexisted with rival stalkers, ones devising breakthroughs far outweighing brute force or bulk. In those same domains where eurypterids held sway, fish populations stirred with a subtler shift, a redesign of their forms that would forever alter the vertebrate saga. From shark forebears to songbirds and even the humans destined to unearth their bones. Well before eurypterids ballooned to enormity, seas hosted an altogether different vertebrate breed. The earliest ones were modest sorts, unarmored, diminutive, missing the jaws that marked later kin, devoid of biting teeth, chase-driving muscles, or defensive plating against shared foes. Their key asset was a notochord, a supple cartilaginous spine along their frames, granting backbone and enabling the side-to-side propulsion modern fish employ. This basic adaptation, emerging in the Cambrian or possibly prior, ranked among life's pivotal leaps. All vertebrates today, hagfish, hummingbirds, humanity, descend from those primordial jaw-free swimmers. Come the Silurian, their offspring had splintered into a dizzying array of shapes, mostly bound by one trait: bony armor. Dubbed ostracoderms by experts, these plated, toothless swimmers sprouted head shields and scales, often encasing their full length, turning them into fortified fortresses that sacrificed agility for unbreachable defense. The protective coverings varied across these groups in form and design. Certain kinds sported intricate cranial plates, resembling full-faced helmets, whereas others featured multitudes of small, interlocking scales forming a supple, yet tough outer layer. Regardless of the exact setup, the underlying purpose rang true: survival in a predator-filled realm, hinged on defense. Among the most common of these shielded swimmers were the thelodonts, whose remains appear in Silurian strata across all principal landmasses. Rather than broad bone shields, they were clad in countless minuscule, tooth-shaped scales, known as denticles, structures akin to those adorning the hides of today's sharks. This setup lent the thelodonts a coarse, abrasive surface, akin to sandpaper, that would deter any hunter from gulping them down easily. Typically modest in size, seldom surpassing 30 centimeters long, these creatures inhabited the floors of nearshore waters. Their broad, flattened forms and underslung mouths point to existence rooted in, sifting through mud for bits of organic matter. The osteostracans adopted a contrasting strategy for their shielding. These swimmers evolved enormous bony plates enveloping their forward sections, yielding a shovel-like profile that's unmistakable in the fossil record. Beyond mere safeguarding, the head plate integrated a suite of detection mechanisms, providing these fish with an exceptionally sharp awareness of their surroundings. Channels akin to the lateral lines in contemporary species crisscross the plate's exterior, picking up waterborne tremors. Certain varieties boasted clusters of minute openings, potentially tuned to electric signals, enabling them to sense the twitches of hidden quarry. Trailing the armored front, the rear was sheathed in lapping scales and driven by a tail that oscillated side to side in the classic piscine rhythm. In the seas off ancient China and Vietnam, an oddly isolated clade of jawless vertebrates was taking shape. Galeaspids crafted headplates even more ornate than those of osteostracans, sporting odd contours like U-shaped arcs, drawn-out snouts and side spikes that evoked antlered headgear on some forms. A lone, prominent vent atop the skull functioned dually as a nasal passage and inlet for water, a setup exclusive to this lineage among all backboned animals. Galeaspids remained restricted to their Asian origins, their relics limited to a compact zone within the ancient South China Craton. Such seclusion renders them crucial for researchers probing how landmass layouts shape the development and spread of primordial vertebrates. Heterostracans completed the primary roster of Silurian jawless fishes, with their traces especially plentiful in the formations of what are now Laurentia and Baltica. These bore plating of unique osseous slabs that fossilized splendidly, their exteriors etched with grooves and nodules, imparting a signature feel to each type. In contrast to the intricate detection-equipped shields of osteostracans, heterostracans sported planar gear, compensating through sheer variety. By the close of the Silurian, they had branched into scores of forms, filling niches from inshore shallows to offshore depths. Jawlessness marked all of them, a seemingly crippling drawback that merits reflection on their endurance and success over millions of years bereft of biting capability. Success stemmed from an array of foraging tactics tailored to diverse edibles. Numerous acted as bottom scrapers, employing round or narrow mouths to suck up seafloor organics like ambulatory vacuums. Some functioned as strainers, pulling in currents to snag minuscule edibles via their gill apparatuses. Others might have parasitized bigger hosts, scraping at tissues with rasping tongues studded in denticle-like spines, echoing the habits of present-day lampreys. Jaw deficiency didn't equate to scant ecological roles. It merely channeled variety into novel paths. Imagine observing these swimmers in their routines amid the coastal basins of Silurian Laurentia. You'd witness an ecosystem governed by alien principles compared to modern seas. The plated ostracoderms glided languidly over the bottom, far from the agile hunters of today. Instead, they foraged and foraged on carrion, burdened by weight that curbed agility but ensured safety, their non-jawed maws restricting them to passive nourishment. Above, Eurypterids prowled the water layers, and the ostracoderm's chief shield against such behemoths was sheer inedibility. overly spiny, cumbersome to ingest, scarcely worth pursuing amid easier targets. However, the realm of these plated herbivores and suction-feeding, jawless creatures was on the cusp of transformation. In the Silurian oceans, likely along shallow shorelines where foraging resources were fiercely contested, some fish species were evolving in ways that would forever alter the vertebrate family tree. The cartilage frames bracing their gills were shifting, curving toward the front, connecting in novel patterns that enabled them to swing apart and together. Across countless millennia, these adapted gill supports would evolve into a groundbreaking feature, a pivoting mechanism suited for seizing, nipping, and grinding. Jaws were emerging, ushering in a revolutionary mode of vertebrate existence. No overstatement here. The jaw stands as the pivotal breakthrough in vertebrate history. Just think about all that jaws enable. They let creatures snap at food, hold it tight, rip it apart, or process it thoroughly. These are basic survival moves we take for granted in our daily lives, seldom pondering existence without them. Whether you're savoring a bite, uttering a phrase, or grinning at a dear one, those motions trace back to gill bars from long-ago fish gliding through Silurian waters. Far beyond adding another gadget to the vertebrate arsenal, jaw evolution unlocked fresh survival strategies, untapped niches, and boundless adaptive paths, paving the way for the incredible array of jawed vertebrates we see today. Sharks and rays, ray-finned fishes, plus the amphibians, reptiles, birds, and mammals. And yes, the very mammal tuning into this narrative at the moment. The building blocks for such a shift were already there in those ancient jawless forms, ripe for reconfiguration. Primitive vertebrate gills relied on a lineup of cartilaginous bars, arched frames that kept the breathing slits unobstructed and anchored the muscles driving water flow over the oxygen-exchanging tissues, positioned in matching sets on either side of the neck. These bars formed a uniform chain of bone-like parts that selection pressures could tweak separately or together. During the early Silurian, the foremost pair of these began to evolve differently. Rather than just propping up gills, they curved inside and linked up, creating a jointed setup that could gape and shut. This shift unfolded slowly, spanning eons as evolutionary forces refined those gill bars into proto-jaws, complete with top and bottom sections meeting at a pivot, powered by robust muscles. By today's measure, those initial jaws were rudimentary at best, basic grippers, not yet tuned for specific diets. Yet even these basic versions provided massive edges over a filter-feeding setup. Jawed fish could snatch quarry outright, rather than just inhaling it. They might shear off chunks too bulky to gulp down. They could even lash out at threats in retaliation. Such perks sparked rapid diversification among jawed species, letting them claim habitats off-limits to their suction-only forebears. Alas, the fossil trail for this pivotal shift is spotty, riddled with lengthy voids between the first whispers of jaw elements and the debut of true-jawed forms. For years, researchers argued over the timing and locale of jaw origins, piecing together scant clues open to varied readings. That changed in 2022, when findings from China revolutionized our grasp of primal vertebrate development. A group from MJU unveiled exceptionally intact fossils from early Silurian strata in Chongqing, remains capturing the intricate builds of fish from roughly 439 million years ago, mere millions of years post the End-Ordovician wipeout. Standout among them was Chianotis duplicis, a diminutive swimmer whose dentition marks the earliest known sign of jaws. its minuscule teeth, needing magnification to spot, clearly bespoke a jawed vertebrate design. Nearby finds showcased hybrids of traits unseen until now, creatures that muddied lines between categories once deemed separate. Take Xenosteus mirabilis, a mere 3-centimeter specimen blending placoderm, shark, and bony fish traits, in a patchwork implying the chief jawed vertebrate branches hadn't yet solidified. These Chongqing treasures offered glimpses into an era when jawed fish were just launching their explosion, their foundational forms, still malleable and innovative, on the verge of ruling seas for the ensuing 400 million years. From the initial trials in evolution, 2 primary lineages of jawed fish arose to rule the Kuran oceans. Placoderms were the pioneers in evolving sturdy jaws. They featured heads and thoraxes shielded by overlapping bone plates, lending them a heavily armored look akin to the ostracoderms they were supplanting. Yet, in contrast to those ostracoderms, placoderms possessed the ability to bite effectively. Their jaws consisted of honed bone edges, functioning as cutting shears, adept at tearing into soft tissue or breaking open shells. During the later Kuran phase, placoderms evolved into numerous varieties, spanning tiny seabed inhabitants to sizable hunters patrolling the edges of reefs. Acanthodians, on the other hand, followed a distinct evolutionary route. Often inaccurately dubbed spiny sharks, these were no true sharks whatsoever. They surfaced scores of millions of years prior to the advent of actual sharks, and their ties to contemporary fish lineages continue to spark debate. Acanthodians stood out due to the spines reinforcing their fins, bony spikes protruding from their forms, possibly acting as defenses against threats. Their skins were clad in compact, square-like scales that interlocked like paving stones, while their prominent eyes hinted at a dynamic, site-dependent way of life. Among the earliest jawed fish, Acanthodians began exploring inland waters, with their remains found in fluvial and lacustrine layers alongside oceanic ones. The arrival of jawed fish dramatically shifted the balance within ocean habitats. Vertebrates now had the capacity for proactive hunting, moving beyond mere filtration or scavenging. They vied head-on with arthropods such as eurypterids for food resources. In the long run, they emerged as fierce rivals. The massive sea scorpions, which had reigned over the Silurian, gradually waned across the Devonian and ultimately vanished as jawed fish proliferated into countless forms, filling every conceivable role in the ecosystem. Observing the Silurian seas would have revealed a gradual handover of power. The former overlords lingered with considerable might, yet the newcomers were already embarking on their enduring rise. Beyond restructuring ocean food chains, the Jaws innovation paved the way for all subsequent developments in animal life. The jawed fish that would one day step ashore to pioneer amphibians descended from this era. The reptiles that would command the Mesozoic, the mammals that succeeded them as Earth's heirs, the birds soaring overhead now, all trace their roots to those pioneering jawed swimmers in Silurian depths. Each time you part your lips to talk, dine, or inhale, you're employing an adapted form of the foundational jaw design that debuted in finger-sized fish over 400 million years back. However, the jaw wasn't the sole upheaval transforming the Silurian realm. As aquatic life innovated through fish, an equally profound shift unfolded overhead in the atmosphere, reshaping opportunities for terrestrial existence. For much of Earth's past, dry land functioned as a zone of death. Not primarily due to hunters, extreme climates, or water scarcity, though these would test the initial land dwellers, but owing to a subtler peril, invisible and imperceptible until harm had set in. The sun unleashed ultraviolet rays in doses deadly to any intricate life form daring the bare ground. Aquatic realms provided a shield, as UV light barely pierced beyond the ocean's surface layers before dissipating. Yet, continents stood defenseless beneath a constant assault of intense radiation that ravaged genetic material, dismantled proteins, and rendered land-based life all but unattainable. The culprit? Oxygen, or more precisely, its scarcity. Today's air includes oxygen that, at stratospheric heights, captures UV radiation, converting into ozone, a trio of oxygen atoms rather than the standard pair. This ozone forms a sparse shield about 15 to 35 kilometers up. Even condensed to ground-level density, it would span just millimeters, but it blocks nearly all of the sun's most hazardous UV frequencies. Absent this layer, Earth's surface would face total annihilation by rays. With it, organisms thrive under open skies, basking in light without lethal consequences. The ozone shield wasn't a constant feature. Across Earth's initial 2 billion years, free oxygen was scarce in the air. Whatever photosynthetic pioneers generated was swiftly bound up in reactions with iron and similar substances. Approximately 2.4 billion years ago, the Great Oxidation Event unfolded as cyanobacteria surpassed the oxygen-absorbing mechanisms, allowing free oxygen to build up in the atmosphere for the first time. One might assume the ozone layer emerged right away, paving the way for life to spread across the continents. Yet, the reality proved far more intricate. Modern studies indicate that even after oxygen surfaced, Earth's ozone stayed erratic for close to 2 billion years, blocked from building up by an unexpected factor: iodine. Compounds of iodine, emitted from the seas, ascended into the air and neutralized ozone nearly as quickly as it formed, establishing a relentless loop of creation and breakdown that never let the ozone reach shielding concentrations. This interplay between iodine and ozone endured for an unimaginably long period, rendering the continents largely inaccessible to advanced life forms even while the seas brimmed with ever more intricate creatures. It wasn't until about 500 million years ago, when atmospheric and oceanic chemistry at last settled into a fresh balance, that the ozone layer achieved steady levels offering real defense against ultraviolet rays. The coincidence is remarkable. This shift happened precisely when the earliest complex life started emerging on land. By the Silurian era, the atmosphere had surpassed this vital point. Oxygen concentrations had climbed to around 10 to 15% of today's figures, sufficient to produce and sustain an ozone shield that filtered out the deadliest UV rays. Though not as strong as current conditions, it still worked. After 4 billion years of Earth's existence, intricate organisms could finally endure in the open atmosphere without succumbing to deadly unseen light. The gateway to the land, sealed since the planet's birth, had begun to swing ajar. This might appear as a mere scientific footnote, a snippet of air chemistry distant from the sweeping tale of life's development, but reflect on its real-world impact. Prior to the ozone steadying, any creature straying beyond the water's surface endured swift and building harm to its inner workings. Algal mats could persist in the intertidal splash areas, shielded by pigments and quick cell turnover, yet more elaborate forms couldn't gain a foothold. Once the ozone settled, the game shifted abruptly. The sun, once a deadly foe, turned into just a hurdle to overcome, a power source for photosynthesis instead of an unending attack on life's essence. The pioneers who would seize this fresh chance were already thriving in Silurian waters in intertidal zones and estuaries where they routinely encountered air. Algae and cyanobacteria had spent ages claiming the watery fringes, creating mats and coatings on stones that tides occasionally uncovered. Certain types had acquired pigments for extra UV defense, like orange and red substances that soaked up harmful rays before they hit vital cell parts. Others had gained speedy DNA repair systems to mend radiation harm almost instantly. These traits, honed across hundreds of millions of years along the waterline, would be crucial for the impending land takeover. Imagine standing on the Silurian Laurentian shore. You'd witness a landscape on the cusp of change. Tidal zones would glow with hues, greens, browns, and rusty oranges, from microbial clusters gripping moist stones. In protected estuaries, the shoreline would merge into a hybrid realm, part sea and part land, where life sampled the upsides and downsides of each. The sun above would seem familiar, warming your face and dazzling your sight, betraying no hint of the unseen barrier that rendered its heat tolerable now. Everything was in place. The ozone had steadied. Edge habitats teemed with life primed for air exposure. Vast, barren continents lay beyond like empty canvases eager for marks. What followed started as cautious trials in select coastal marshes. Yet it would reshape Earth's surface more deeply than any prior milestone in life's saga. The initial real plants were on the verge of anchoring into dirt, launching the world's verdant era. No primeval woods stood yet. No early fields, no pioneering grass shoots, no blooms, no wide leaves to throw shade. Nothing like that had graced Earth before. In the Silurian colonization of land, these plants scarcely resembled anything we'd call plants today. These early land plants lacked roots to secure them in the earth, leaves to harness sunlight, or seeds to scatter their progeny far and wide. Instead, they featured a far more essential feature: vascular tissue, an intricate network of internal conduits that moved water throughout the organism. This seemingly simple breakthrough was the crucial element that opened up the land masses for colonization. Absent this vascular system, vegetation was limited to spots where moisture was readily available, such as damp stones, stream banks, or air thick with vapor, allowing every cell direct access to hydration. But with it, plants could draw water up from below and distribute it internally, enabling them to reach greater heights, expand their reach, and thrive in areas distant from any pools or rivers. Among the initial vascular trailblazers was Cooksonia, a diminutive and unassuming organism that one could easily overlook if it grew nearby. The biggest discovered remains reach about 6 centimeters in height, comparable to your thumb, and typical examples were much tinier. The whole structure was just a forking stem that split into Y-like branches, each tip bearing a small rounded sporangium for generating reproductive spores. There were no true leaves, blooms, or roots as we know them today. Only those slim, verdant stalks emerging from the wet soil, repeatedly dividing until they ended in spore-producing points. Cooksonia received its name from Isabel Cookson, an Australian paleobotanist who devoted years to researching the planet's first terrestrial flora. It was officially documented in 1937, based on specimens unearthed in Wales and Scotland. Afterward, Fossils have appeared in Silurian strata across all principal landmasses, highlighting the rapid expansion of these basic plants after securing their place ashore. The most ancient verified Cooksonia remains hail from the Czech Republic, aged around 425 to 427 million years old, situating them squarely in the Wenlock epoch of the Middle Silurian. Yet scattered spores and partial stems indicate that vascular flora might have tested land living sooner, possibly reaching back to the Ordovician, although such findings are still debated. Imagine crouching near a live Cooksonia during the dim glow of a Silurian day, scrutinizing its form. You'd spot a vital detail in its build. At the heart of every stem ran a shadowy band of tissue, appearing as a fine streak in a crosswise slice. This vascular bundle formed the plant's inner waterway, built from specialized tracheids cells that had developed the capacity to convey water upward, defying gravity's tug. These cells' walls were strengthened by lignin, a resilient organic substance that offered rigidity and stopped them from imploding under the suction of ascending moisture. Over time, lignin emerged as one of Earth's most plentiful organic materials, crafting the wood in forests and piling up into massive layers that later turned into coal seams. Cooksonia also had stomata, tiny adjustable openings along its stems that manage gas flow with the air. Open stomata let in carbon dioxide for fueling photosynthesis, while releasing oxygen as a byproduct. Closed ones helped retain moisture, curbing the inevitable loss through evaporation that came with exposure to dry winds. The advent of stomata addressed a core hurdle for life on land, acquiring atmospheric carbon dioxide without drying out entirely. Virtually every plant you've encountered, whether the turf underfoot or a soaring sequoia, relies on the strategy Cooksonia devised over 400 million years past. The landscape Cooksonia called home wasn't completely desolate. Microbial films and layers had already claimed the borders of aquatic zones, creating slim coatings of light-capturing life that bound sediments and enriched the nascent dirt. Moss-like and liverwort-like forms could have existed too, despite their faint traces in fossils from that era, owing to their soft bodies that rarely endure in stone. Cooksonia's edge lay in its vertical growth, elevating it over rivals for sunlight and letting wind carry its spores, independent of water for propagation. These traits appear humble, yet they propelled vascular plants to supremacy in land-based greenery in mere dozens of millions of years. Cooksonia likely represented not one species, but a stage of development, a shared structural milestone that various plant lines reached separately while adjusting to continental existence. Certain Cooksonia-like plants likely served as forebears to the lycophytes, the lineage encompassing today's club mosses. Additional branches might have spawned entirely separate evolutionary paths, with their offspring developing traits that emerged distinctly only during the Devonian and subsequent eras. These preserved remains capture bold trials in adapting to dry land existence, ventures that thrived in some cases or faded into oblivion in others. Everyone groped tentatively toward an uncharted realm untouched by any vegetation prior. In Australian deposits, experts have unearthed remnants of Baragwanathea, a flora far more intricate than Cooksonia, emerging from strata of comparable or marginally earlier vintage. Baragwanathea featured genuine foliage in the form of petite, scale-resembling appendages twisting along its stalks. enabling it to reach elevations around 25 centimeters, dwarfing its more rudimentary peers. Its occurrence within the Silurian strata has long baffled experts, appearing overly sophisticated for that era, akin to discovering a modern cell phone amid displays of early telegraphic devices. Certain scholars challenge the chronology of the enclosing sediments, proposing they could date to a later phase than first estimated. Alternative views contend that botanical advancement during the Silurian unfolded more rapidly and innovatively than long accepted, with diverse clades surging toward sophistication via concurrent routes. Regardless of the exact chronology, the Silurian era witnessed vascular flora, securing enduring footholds in the land-based realm. These pioneers stuck to humid zones close to aquatic edges. Without developed root systems, their expansion away from rivers and bogs stayed severely restricted. They stayed diminutive, basic, and prone to being dismissed. Yet, they had breached an irreversible boundary. After 4 billion years of stark, lifeless terrain, the continental fringes began to sprout verdant hues, and in the wake of flora, fauna were bound to trail. Vegetation claimed primacy, though solitude wouldn't endure. Mere millions of years after initial vascular species rooted in seaside marshes, novel entities started traversing the soggy boundaries separating ocean from shore. These invaders scuttled on numerous limbs, 6, 8 scores, even hordes, and ushered in a transformative shift in creature biology, every bit as pivotal as botanical breakthroughs. For the initial instance in earthly life's chronicle, beasts inhaled atmosphere outright, drawing vital oxygen via dedicated structures unprecedented in watery domains. Arthropods had colonized the mainland, destined to stay. Shifting from aquatic to aerial surroundings posed hurdles unlike those for flora. A creature can't merely root in place to draw sustenance from its surroundings. It demands mobility to hunt nourishment, evade threats, seek partners, pursuits all fueled by energy, which hinges on oxygen uptake from the encircling element. Aquatic environments rely on gills for this, their fragile lamellae permitting dissolved gas to seep straight into circulation. Yet in atmosphere, such gills fold uselessly, their fine threads clumping sans buoyant liquid. Even structurally intact, they'd struggle with air's far denser oxygen levels, demanding fresh adaptive strategies for optimal processing. Arthropods devised the tracheal network as their fix, an intricate web of inner conduits channeling atmosphere from body surface ports straight to oxygen-hungry cells. These entry points, termed spiracles, remain visible along the flanks of contemporary insects and assorted land-dwelling arthropods, modest orifices funneling into ramifying channels that taper onward to singular cells. Gas seeps through via diffusion alone, bypassing any circulatory fluid transport. This straightforward, refined design excels particularly for compact forms. The emergence of spiracles and tracheal conduits unlocked genuine land independence for arthropods, eliminating any compulsion to revisit water for gas exchange. The earliest traces of such aerial gear stem from a specimen in Silurian formations close to Stonehaven, along Scotland's northeastern shore. Pneumodesmus newmani resembled a millipede or kin and inhabited the scene roughly 430 million years back in the late Wenlock or early Ludlow phase. The specimen is minuscule, a mere sliver of integument under 1 centimeter, yet etched upon it lie clear spiracles. These respiratory vents confirm its status as an atmospheric breather. This modest exoskeletal shard stands as the prime direct token of land-based breathing yet discovered. It verifies that arthropods had cracked aerial respiration by mid-Silurian times. Pneumodesmus functioned as a detritivore, subsisting on decomposing remnants rather than pursuing fresh quarry. Such a niche aligns well with a pioneer settler in this novel domain. Initial land-based ecosystems were straightforward setups, without the intricate networks of interactions seen in today's habitats. Fallen plant debris, layers of bacteria, fungal patches, and algal coatings served as the main sustenance for the pioneers of terrestrial life, and millipedes were perfectly equipped to make use of them. With their abundance of limbs, they could traverse rough ground effectively. Robust outer shells shielded them from drying out, while their guts handled the fibrous, cellulose-packed parts of primitive land vegetation. Acting as decomposers, they dismantled organic waste and fed essential elements back into the nascent, fragile dirt layers emerging on the surface. However, millipedes weren't the sole arthropods shifting to dry land. Evidence from the closing stages of the Silurian, especially at Ludford Lane in Shropshire, England, indicates that ground-level habitats had reached an unexpected degree of sophistication by about 414 million years ago. Discoveries at Ludford Lane include not just detritivores but also hunters, specifically at least 2 centipede varieties and a trigonoterid arachnid, a long-extinct kin to spiders. Such carnivores point to available victims, signaling an operational chain of feeding relationships across various levels. These organisms weren't lone trailblazers barely holding on in a strange world. They formed parts of mature groups, habitats that had evolved over countless years prior to the Ludford Lane layers capturing a glimpse of their world. The centipedes from Ludford Lane functioned as stalkers, their sleek forms and array of legs tailored for chasing targets amid the debris of leaves and cracks in the ground of nascent land areas. In contrast to millipedes, which sport 2 leg pairs per segment and advance in leisurely wavy motions, centipedes feature a single pair per segment and burst into rapid motion to catch food or flee threats. Their foremost appendages had transformed into poisonous claws known as forcipules, designed to deliver paralytic venoms into tinier arthropods. Finding these expert hunters in the Silurian shows that moving onto land wasn't a cautious or incomplete endeavor. It represented a bold advance, with creatures already developing the precise tools required to track and dispatch in the fresh ground setting. Trigonoterid arachnids proved just as imposing as predators, albeit employing a distinct approach. Linked to contemporary spiders, yet from a distinct branch, these beings possessed 8 legs and a plated, segmented rear body shielded by tough skin. Silk production eluded them. That would emerge later in actual spiders, but they excelled as lurkers, lying in wait to seize passing smaller arthropods with their clutching pedipalps. Imagine strolling across the marshy shores of late Silurian Laurentia, minding your steps between Cooksonia stalks and liverwort coverings. You could have spotted these primordial stalkers poised in quiet anticipation, ready for an unsuspecting victim to cross their path. Primitive scorpions appeared in the Silurian too, but their tie to land remained unclear. Numerous Silurian scorpions still had book gills instead of book lungs, hinting at a mainly watery lifestyle or reliance on extremely damp spots. They likely represented intermediate stages, able to venture briefly onto shore, but not fully adapted yet. Remains appear in both saltwater and riverbed rocks, with certain examples from layers indicating tidal zones where air exposure happened routinely. Eventually, certain branches finished the shift, transforming book gills into book lungs that enable today's scorpions to endure in arid regions worldwide. As the Silurian drew to a close, the framework of land ecosystems started to take shape. At the bottom were the foundational producers, basic vascular flora, and the preceding microbe films, supporting the feeding structure. Detritivores, such as millipedes, handled decaying material, reusing vital compounds and aiding in building up Earth. Carnivores, including centipedes and trigonopterids, pursued the detritivores and one another, introducing further depth to the arrangement. Though it paled beside the lush land systems of the Devonian and beyond, the groundwork was set. Organisms had secured a lasting foothold on dry ground with no turning back to the oceans. Arthropods demonstrated the continent's livability, yet they navigated a planet still shifting. The flora upholding those initial land setups stayed diminutive and limited to humid zones, while the ground cover was meager and nutrient scarce. Terrestrial life had far fewer opportunities for growth than the abundant habitats in the seas. However, while these initial land settlers were securing their foothold, profound shifts were transforming the planet, opening up new prospects for terrestrial existence. Land masses were smashing together, towering peaks were emerging, and Earth's landscape was undergoing a massive overhaul that would influence weather pattern, sea flows, and the spread of livable zones worldwide. Our planet is always in motion. People often view the Earth under their feet as stable and unchanging, the one constant amid flux. In reality, though, the continents aren't anchored. They drift atop lithospheric plates, gliding over the semi-molten mantle underneath, propelled by convective flows that nudge and tug them along the planetary surface at speeds of just a few centimeters annually. Such a slow pace seems negligible, hardly noticeable, yet across eons those centimeters add up to thousands of kilometers. Seas expand and contract. Land masses merge and split. Ranges of peaks ascend and erode. Earth's terrain is perpetually reshaped. The Silurian era marked a time when one of the grandest phases of this ongoing transformation hit its peak intensity. The build-up to this clash had spanned tens of millions of years prior to the Silurian start. Laurentia, the primordial continent destined to evolve into North America, positioned itself close to the equator, with its eastern edge bordering the Apotus Ocean, a body of water that had been expanding since the late Precambrian. Across that expanse lay Baltica, the proto-continent that would later form Scandinavia and northern Europe, twisting and shifting westward under the same geological drivers that would soon draw it toward collision with its counterpart. Sandwiched in the shrinking space between them was Avalonia, a narrow microplate bearing the stones that would eventually become England, Wales, and sections of eastern North America. The Apotus Ocean was shrinking at a pace invisible to anyone on shore, maybe 2 or 3 centimeters yearly, equivalent to a thumb's breadth lost as the seafloor's edges plunged into the mantle at subduction zones fringing the continents. This relentless devouring of ocean basin pulled the flanking landmasses ever nearer. By mid-Silurian, they were near enough for the true impact to commence. Continental impacts demand compromise, while dense, slender oceanic crust can sink into the mantle for reuse. Continental crust's lightness prevents subduction. It buckles instead. Edge rocks of the clashing landmasses get squeezed, warped, shoved atop each other in vast layers, and altered through intense heat and pressure. The crust bulks up as debris accumulates, then buoyantly elevates, akin to how a laden vessel sinks deeper than a light one. Peaks form, elevated by pressures outpacing erosion, at least temporarily. The range born from the Laurentia-Baltica merger is known as the Caledonides, after Colonia, the Roman term for Scotland. In their prime, they might have matched the present-day Himalayas' stature, though certainty eludes us due to 400 million years of weathering reducing them to remnants. Today's survivors include the Scottish Highlands, Norway's western peaks, Wales's and Ireland's uplands, and the Appalachians' northern stretches, all relics of one immense cordillera, spanning the emerging supercontinent from the smash-up. Gazing over heather-draped Scottish hillsides lets you behold the weathered bases of summits that once pierced the heavens. The merger-reunited stones parted for hundreds of millions of years, formations from ocean-divided realms, each gathering unique fossils over their isolated histories. Geologists deduce the Apatis Ocean's past this way, by spotting Scottish sea creatures mirroring North American ones, yet utterly unlike those in nearby England, merely hundreds of kilometers south. Scotland and England once flanked opposite ocean shores. Their fossil records stood as apart as today's Atlantic and Pacific shores. The join line, a band of severely twisted strata denoting the continent's union, approximates today's Scotland-England boundary. Although the exact path was obscured by subsequent geological upheavals, the creation of this suture zone ensured that, by the late Silurian, Laurussia, Baltica, and Avalonia had fused into one vast landmass, which scientists refer to as Laurasia, or occasionally Euramerica, or the Old Red Continent. This emerging supercontinent extended from tropical latitudes northward into temperate regions. Its heartland was ruled by the weathered remnants of the Caledonian Mountains, along with the waterways that transported their debris to expansive coastal lowlands and river mouths. The reddish hue defining the Old Red Continent stemmed from the iron oxides in these deposits, indicating they formed in oxygen-rich land-based settings. This stood in sharp opposition to the dark, carbon-laden shales that built up in low-oxygen ocean depths. The forging of Laurussia represented merely a segment of a grander tectonic mosaic. Gondwana remained a massive presence in the southern hemisphere, while separate pieces like Siberia, the China Cratons, and minor terrains, familiar mainly to experts, floated independently over the global sea. Yet the crash that birthed Laurussia established a template enduring for hundreds of millions of years. As drifting landmasses gradually united into the supercontinent Pangaea, which would command the late Paleozoic and early Mesozoic eras. The Silurian served as an interim stage in this odyssey, a phase when Earth's layout was shifting but hadn't settled into its ultimate form. Imagine standing along the edges of the fresh Laurussia, gazing toward the nascent Caledonian ranges. You'd behold a terrain caught in flux. Torrents laden with silt cascaded from the elevations, laying down strata of silt and pebbles that later solidified into the Old Red Sandstone, a formation linking Britain, Greenland, and eastern North America. Expanding shorelines opened fresh territories for vegetation and jointed invertebrates starting to claim the shores. Meanwhile, in the near-shore waters flooding large swaths of the land's interior, organisms kept innovating relentlessly, unaware of the crustal movements altering the surface overhead. Those peaks wouldn't endure. Geological constructs never do, not even chains as formidable as the Caledonides. Weathering assaulted them right from their uplift, grinding them into particles hauled to the ocean, where they piled up in river deltas, shoreline flats, and underwater aprons. In just 100 million years, the towering summits would erode into gentle swells, and another 100 million years on, those swells would flatten almost entirely. Still, the impact of that clash lingered far beyond the mountain's demise. The supercontinent it contributed to would steer evolutionary paths for eons, and the twisted, altered stones it produced endure as a testament to its fury, decipherable by geologists even now. As land masses smashed together and ranges ascended, ocean life in the Silurian pursued its separate path, influenced by worldwide and regional dynamics alike. Evolving shorelines reshaped seaflows and weather systems, spawning novel niches and erasing prior ones. Fauna, successful in early Silurian realms, now battled as their surroundings morphed or vanished, whereas some thrived amid the emerging opportunities. The underwater realm was evolving, and the forthcoming saga of Silurian biodiversity would unfold through organisms that adjusted to these shifts. The Silurian oceans teemed with resilient holdovers. Each swimmer, bottom dweller, or floater in those primordial waves bore the scars of calamity, a hereditary endowment forged by the mass die-off concluding the Ordovician. The taxa-ruling Silurian seas weren't mere holdovers from pre-extinction days, carrying on unchanged. They sprang from the fortunate remnants, the bloodlines that squeezed through the crisis as rivals fell away. This gauntlet of endurance remolded them profoundly, both visibly and inconspicuously, yielding ecosystems that operated unlike their predecessors. Brachiopods exemplify this shift vividly. Prior to the wipeout, their assemblages boasted extraordinary variety and strong regional specificity, with varied kinds suited to distinct locales and circumstances worldwide. The event wiped out much of that richness, wiping out whole clans and sparing just a few lines to reclaim the barren seabeds. Yet these remnants displayed extraordinary versatility, following the mass die-off. The pentamerids, known for their robust shells and unique internal bracing, experienced a burst of diversification in the early Silurian. Their offspring quickly dispersed over the continental shelves of all principal landmasses. In just a few million years, you could spot pentamerids thriving in the balmy coastal zones of Laurentia, the shoreline seas of Baltica, and along Gondwana's edges. This core body design thrived in habitats that once supported entirely distinct brachiopod communities. Another striking feature of these Silurian pentamerids after the extinction was their reduced size compared to Ordovician predecessors. They were distinctly and uniformly smaller, as though natural selection had opted for compactness over scale. This trend, dubbed the Lilliput effect, shows up often in fossils post-mass extinctions, even as experts continue to argue over its origins. Smaller body size might help creatures endure lean times with minimal resources, or it could enable quicker breeding, speeding up population rebounds as environments stabilize. Alternatively, the chaos after an extinction event might strip away the rivalries that typically push for bigger forms. Regardless of the reason, Silurian brachiopods were humble in stature relative to their ancestors, crafting shells with a frugality of substance that might strike a casual onlooker as nearly stingy. The tabulate corals and stromatoporoids responsible for the grand Silurian reefs also stemmed from this recovery phase. Their boom owed much to the removal of rivals that had formerly curbed their growth. Tabulate corals had lingered through the Ordovician but played small roles in reef systems, eclipsed by dominant groups hogging prime spots and ideal settings. The extinction shifted the dynamics. Freed from those rivals, tabulate corals ventured into fresh ecological slots, allying with stromatoporoid sponges to lead reef building for the subsequent 100 million years. These reefs weren't mere echoes of prior ones. They represented fresh architectures, novel associations, and innovative arrangements of ocean life rising from the ruins of the past. Crinoids offer a parallel tale of endurance and proliferation. These elegant echinoderms, featuring delicate arm-like rays and sturdy stalks rooting them to the bottom, outlasted the extinction better than most seafloor dwellers. About 70% of crinoid genera endured into the Silurian, a survival figure that many other clades would covet. Unburdened by extinct competitors, crinoids proliferated over the world's mending continental margins, creating thick carpets on the ocean floor that sifted nutrients from the currents and sheltered myriad tiny life forms. In certain Silurian layers, crinoid remains are so plentiful, they define the stone itself, with their round stem sections stacked in heaps several meters deep. Not every lineage bounced back so strongly. Trilobites, the emblematic arthropods ruling Paleozoic seabeds since the Cambrian, failed to fully rebound from the Ordovician-Silurian crisis. They suffered severe blows, with whole families and key branches vanishing over mere millions of years. The remnants did branch out somewhat in the Silurian, occupying voids left by lost kin, yet they never recaptured their former variety or sway over ecosystems. Tally the trilobite species from the Ordovician, then recount them in the Silurian, and the drop would hit you right away. Slimmer variety, simpler shapes, fewer trilobite lifestyles. They persisted, even clustering thickly in spots. But theirs was a fading reign, clinging to the frayed edges of a realm eroding since Cambrian times. Among Silurian trilobites, Calamene stood out as a standout, its traces so widespread in specific strata that it later became Wisconsin's state fossil. This modest trilobite, seldom topping 10 centimeters long, boasted a special trick: coiling into a compact sphere under threat, shielding its soft belly with a fortress of tough exoskeleton. Midwest American rocks capture endless Calamene examples locked in death, from outstretched poses to fully curled ones, a record of existence edged with vigilance against lurking perils. Cradling a Calamene fossil means grasping the echo of a creature that navigated sunlit, predator-packed shallows over today's Illinois and Wisconsin. Graptolites kept experiencing a steady downturn throughout the Silurian, yet they stayed vital for researchers aiming to pinpoint the age of the rocks containing them. These colonial beings, known for their frequent saw-blade-like fossils in Silurian shales, had boasted far greater variety back in the Ordovician, when they dominated the plankton world with shapes from basic single branches to intricate coiled clusters. The mass extinction had slashed that variety sharply, sparing just a handful of lineages to persist into the Silurian. Distinct graptolite types define each phase of the Silurian. Parachaetographus acuminatus in the initial Landovery, Sotographus centrifugus during the Wenlock, and Monograptus perultimus toward the close. Their evolving shapes offer geologists a reliable sequence for matching rock layers across global sites. Among mollusks and various other sea invertebrates, comparable cycles of waning and rebound unfolded, shaped by each group's unique challenges. Gastropods and bivalves made it past the extinction and expanded in the Silurian. although their current supremacy wouldn't emerge for many millions of years more. Nautiloid cephalopods, those coiled and straight-shelled kin to today's nautilus, roamed the Silurian oceans as agile hunters, snaring food with tentacles and darting via jet bursts through the depths. Bryozoans bounced back from the die-off, but with a fresh lineup. Certain Ordovician lineages vanished completely, while others spread into vacated roles. The broader scene shows habitats in constant shift, with ecosystems still reorganizing in the wake of a disaster that had upended ocean biodiversity. This reorganization wasn't haphazard. The creatures that flourished in the Silurian were those ideally adapted to the post-extinction environment. Versatile feeders tapping diverse food sources, fast reproducing pioneers claiming barren areas, and tough holdouts whose features aligned with emerging survival demands. Evolution doesn't foresee or prepare for looming threats. It just boosts what succeeds right now. And the Silurians now boosted life forms worlds apart from the Ordovician's rulers. This handover in Silurian ocean dwellers echoed a recurring theme after every major extinction on Earth. The Undurees claim a stripped-down planet brimming with potential, branching out to occupy voids in manners unthinkable, before the event cleared out rivals. The Silurian oceans served as an evolutionary workshop, sketching designs for tomorrow's sea networks, while the prior sketches were barely set. And buried in those waters, amid sediments building up in coastal lows and continental edges, another element was taking shape, one whose significance would stay hidden for eons until people bored into old strata for fuel to drive today's society. Far below the ocean bed in lightless voids, the deceased were stacking high. This isn't mere metaphor. In select basins fringing Gondwana and in the profound reaches of narrowing seas, organic debris built up in volumes hard to grasp. Corpses of endless plankton, graptolites, algae, bacteria, the myriad tiny players anchoring Silurian food chains, sank slowly from above, layering the seabed season by season, era by era. Typically, such a steady fall of organics would fall to scavengers and rotters, looping back into the sea's nutrient flow. But conditions here were far from typical. Those basin floors lacked oxygen, barren of the air vital to nearly all organisms. In that choking gloom, the remains lay untouched. What followed were black shales, stones so inky they devour illumination, their hue signaling the trapped carbon from life. Spotting black shale in a cliff face or display case means gazing at packed mortality, ages of life's output crushed into rocky strata. The organics lending these stones their signature look have endured heat and squeeze across vast geological time, their intricate biostructures dismantled and reforged into basic substances. Certain of those substances ring familiar to drivers pumping fuel or folks warming houses with natural gas. The dark shales from the Silurian era serve as source rocks, the underground layers where oil and natural gas originally formed before moving to the reservoir formations we tap into now. The largest Silurian dark shales built up along the northern border of Gondwana, forming a wide band that ran from present-day North Africa across the Middle East and into the Arabian Peninsula. In the early Silurian, this area sat at the southern side of a contracting sea, where poor water flow and abundant life teamed up to foster ideal settings for saving organic material. The depths were sufficient to block sunlight from the sea floor, stopping photosynthesis from oxygenating the deeper zones. The basin was somewhat sealed off, curbing the entry of oxygen-rich water from the broader sea, while the upper layers thrived with nutrients rising from below, fueling massive growths of light-capturing plankton. Graptolites played a key role in piling up these carbon-heavy layers. Their group-based structures made of proteins and various organic materials dropped to the bottom in huge quantities after colonies perished. The signature saw-edged remnants that help date Silurian strata turn up mostly in these dark shales. Their fossils stayed remarkably intact thanks to the oxygen-poor environment that halted decomposition. In certain layers, graptolite fossils crowd the stone so densely that they make up its main part. Shadowy streaks on a shadowy canvas, evidence of the innumerable trillions of group-dwelling creatures that thrived and faded in the overlying seas. In our time, these old layers lie beneath some of the planet's richest oil areas. The Silurian dark shales of North Africa, dubbed hot shales due to their rich organics, supply 80 to 90% of the region's Paleozoic fuels. The hydrocarbon reserves in Libya, Algeria, and Egypt pull their value from seafloor buildup over 400 million years back, when graptolites floated in vanished oceans over terrains yet to form their current outlines. Comparable layers exist in Saudi Arabia and Jordan, where Silurian source rocks feed into oil networks that have influenced worldwide trade and politics beyond the wildest dreams of their tiny builders. Turning organic-packed sediments into oil happens across vast geological eras, needing precise levels of heat, squeeze, and depth of cover. Right after deposition, the Silurian dark shales were just sludge. Gloomy, organic-loaded sludge, sure, but still sludge. Through eons, as more layers piled on top, they sank further, squeezed by the burden of upper rocks and warmed by the planet's core heat. At temp from about 60 to 120 degrees Celsius, the organics inside started changing. Elaborate life molecules split into basic hydrocarbons. The extended chains and cyclic forms of oil elements emerged from the husks of beings long gone by hundreds of millions of years. Known as catagenesis, this shift marks the vital phase that turns organic-laden stone into an oil generator. Not every bit of organic stuff in a dark shale turns to liquid or vapor fuel. Plenty stays trapped as kerogen, a sticky organic goo that demands even hotter conditions for full breakdown. Yet catagenesis yields enough hydrocarbons for viable oil amounts. Assuming the rocks align favorably elsewhere, the fuels need to seep from the source into spongy reservoir stones to pool in usable amounts. They require sealing caps of non-porous barriers to keep from leaking out, and they have to endure for hundreds of millions of years, dodging damage from extra heat, wear, or other Earth shifts. Should you ever power a vehicle, soar on a flight, or warm your house with pipeline gas, it's quite possible that portion of your power traces back to Silurian waters. The organics gathered in those primeval oxygen-scarce hollows have come a far way to fill your tank. From alive forms to heaped muck, from muck to solid stone, from stone to generating layer, from generating layer via travel routes to storage zones. And at last, from storage via drills and lines to the burn that frees the power held in those primordial molecular ties. 400 million years of planetary tale link the graptolites of the Silurian to the daily drive of someone in the 21st century. There's an eerie quality to this link, underscoring how our contemporary society relies on the fossilized remnants of creatures so profoundly old that they existed before jawed fish leafy plants, or air-breathing animals ever appeared. Our economy, fueled by petroleum, rests upon the bedrock of geological epochs, tapping into stockpiles that formed over vast stretches of millions of years, only for us to burn through them in just a few centuries. Is this a prudent path? Is it viable in the long run? Should we pivot to other options? The Silurian graptolites offer no solutions to these dilemmas. All they provide are their altered relics, reshaped by eons of compression and heat into the energy source driving the society we've constructed. Yet the dark shales represent merely a single facet of the Silurian's enduring impact, a single glimpse into an era whose echoes linger throughout today's landscapes. Elsewhere in rocks from that distant time, other portals reveal alternate tales. These are preserved scenes of ancient habitats, etched into stone as vivid captures of bygone moments, enabling us to vividly revive the ecosystems of old with astonishing fidelity. The fossil record, however, falls far short of a full catalog of prehistoric organisms, a fundamental truth that paleontology imparts and one of its key insights. Most species that once roamed the earth vanished without a whisper, their fleshy forms devoured by predators and bacteria, their fragile forms eroded by the sediment's acids, their molecules repurposed into fresh cycles of life. Fossilization demands a rare convergence of events: swift entombment, ideal geochemical settings, durable elements that can harden into minerals, and then a stroke of fortune over millions of years, as the enclosing strata withstands weathering, transformation, and the countless forces that obliterate far more records than they safeguard. The specimens, housed in museums and labs, don't mirror the breadth of ancient biodiversity. Instead, they form a lopsided assortment, favoring shelled or bony creatures and locales where quick burial and optimal conditions prevailed. Still, around the globe, certain spots emerge where fate conspired perfectly, yielding views into history far sharper than fortune should allow. The Silurian boasts an abundance of such extraordinary locales, sites where exceptional preservation lets us map out prehistoric seascapes with near-miraculous accuracy. Exploring these areas, or poring over their unearthed treasures, brings us tantalizingly near to strolling amid a realm extinguished some 400 million years back. Gotland stands out as the premier Silurian portal. This Swedish island in the Baltic Sea, positioned between Sweden and Latvia, consists largely of Silurian limestone, deposits from vibrant reef habitats that once basked in equatorial tropics. Strolling Gotland's craggy coastlines means treading atop the compacted frames of stromatoporoids and corals, the sturdy bases of thriving communities that persisted for ages until plate tectonics shifted them toward chillier realms. The island's bluffs reveal successive strata of reef growth, letting experts follow the progression of these habitats over time, observing as various species ascended to prominence only to yield to successors. Gotland's scientific allure stems from its array of captured settings. The lower Visby beds document a mesophotic reef world, home to life at about 100 meters deep, where faint light fostered environments, unlike the bright, shallow expanses typically associated with coral gardens. The Högklint Formation captures nearer shore reefs, zones where rays reach the sea floor to nourish light-dependent life. And in more recent layers, evidence points to what could be the earliest known turbid reef setup, a habitat in silt-laden seas where only low-light specialists endured. Such varied preserved niches paint a multifaceted view of Silurian ocean dwellers, illustrating how assorted groups filled distinct roles along the shelf's gradients. In the U.S. Midwest, from Wisconsin to Illinois and Indiana, another Silurian vista unfolds. Here, enduring reef limestones create striking ridges across the countryside, rising like the stony spines of long-extinct marine behemoths. Geologists first documented these structures in the 1800s, marking them as some of the continent's initial identified prehistoric reef complexes. Certain formations consist of small patch reefs spanning only a few dozen meters, whereas others formed enormous edifices extending hundreds of kilometers along the edges of the shallow inland sea that blanketed the continent's heartland. Quarries excavated into these structures lay bare their inner architecture with stunning clarity, showcasing the development of stromatoporoids, the arrangement of coral groupings, and the myriad tiny creatures that occupied every possible role in the reef ecosystem. In England, the strata near Ludlow in Shropshire lend their name to a full geological epoch within the Silurian. The Ludlow series documents a shift from oceanic to more continental environments, featuring fossils from classic sea dwellers to initial signs of terrestrial life. It was at the Ludford Lane locality that scientists unearthed the arthropod collection, demonstrating that intricate land-based habitats had emerged by the late Silurian. The centipedes and trigonotarbid arachnids we met earlier on our expedition. These Ludlow deposits serve as a testament that the Silurian era extended beyond oceanic proliferation. It marked the era when land colonization accelerated, as desolate land masses started evolving into the verdant, vibrant terrains familiar to us now. Scotland holds another vital segment of the Silurian enigma. Outcrops around Stonehaven on the northeast shore have produced Pneumodesmus pneumoni, that minuscule millipede relic whose breathing pores provide the earliest confirmed proof of aerial respiration in any creature. The Scottish Silurian also captures remnants of the odd pre-collision landscape, when today's Scottish rocks lay distant from those in England, across an ocean spanning hundreds of kilometers. Fossils in Scottish Silurian layers align with North American ones, rather than England's, a correlation that clicks only when recognizing that Scotland and England flanked opposite shores of the Iapetus Ocean until the late Silurian fused them. Among the most groundbreaking Silurian discoveries in recent decades hail from China, specifically from sites in Chongqing and nearby areas, reshaping our grasp of primitive vertebrate development. The piscine remains here, Chianidus boasting its dentition, Swanidus displaying its blend of traits, plus diverse galeaspids and anaspids that complete the portrait of Silurian aquatic fauna, have extended timelines for pivotal evolutionary leaps and shown that jawed vertebrate radiation was already advancing strongly by the early Silurian. These Chinese sites owe their value to superb taphonomic settings that retained not only skeletal elements of these primordial fish, but also hints of fleshy parts and fine structural nuances, typically erased by decomposition. Additional Silurian glimpses appear worldwide, each furnishing a unique angle on this bygone realm. Estonia harbors outstanding stromatoporoid reefs in the Katavir beds. The Czech Republic has produced among the most ancient Cooksonia examples, extending the timeline for vascular flora on terra firma. Australia offers Baragwanathia, the intriguingly advanced flora that surfaces in strata seemingly too ancient for its complexity. Every site contributes a further element to the mosaic, a supplementary clue aiding our detailed revival of the Silurian epoch. Should you magically tour all these locales, strolling Gotland's coastlines, delving into Wisconsin's quarries, scrutinizing Ludlow and Stonehaven's exposures alongside Chongqing's, you'd perceive the Silurian less as a monolithic interval and more as a vibrant, evolving sphere. Oceans varied by region. Biotas differed from reef tops to abyssal depths, while the continents morphed from stark stone to nascent vitality. Our archival portals remain patchy and fragmentary. Yet collectively, they afford a peek into an epoch predating any human-like presence on Earth, a foundational era paving the way for all subsequent history. Still, the Silurian couldn't endure indefinitely. Like every geological span, it drew to an end. As eons piled up, transformations mounted that would conclude this phase of planetary chronicle and inaugurate the next. The Silurian's close-lacked drama. Absent were asteroid strikes, massive volcanic outbursts, or abrupt disasters akin to the crisis that launched the period. The shift to the Devonian unfolded leisurely, a protracted reconfiguration of environments spanning millions of years, unlike the abrupt ruptures defining some of Earth's starkest divides. Oceans receded, weather patterns altered. The vast reef complexes that thrived mid-era started altering in form. These ecosystems rearranged themselves to cope with environmental shifts that were understated yet steadily diverging from prior eras. Existence persisted, evolved, and ultimately passed a pivotal point that scientists would subsequently identify as the dawn of another era in the planet's timeline, the Predoli epoch, marking the concluding phase of the Silurian, derives its title from a site in the Czech Republic, renowned for its prominent outcrops of contemporaneous strata. Spanning about 3 million years, it served as a short epilogue to a span exceeding 20 million years overall. In this interval, patterns foreshadowing the Devonian started to emerge. Inland seas that had inundated continental hearts were withdrawing, uncovering terrain submerged since the initial Silurian stages or before. In areas once teeming with varied sea life under balmy, shallow depths, muddy shorelines and inland lowlands now surfaced. Fresh land habitats stood ready for settlement. As oceans receded, they abandoned an unforeseen legacy in the depressed interiors of continents. Seawater, isolated in diminishing lagoons disconnected from broader marine realms, underwent evaporation that intensified its dissolved salts until saturation occurred. Minerals like salt and gypsum started crystallizing from the brine, piling up in substantial strata at the bottom of these desiccating depressions. The Michigan Basin, now buried beneath much of Michigan and neighboring areas, gathered evaporate layers reaching hundreds of meters deep in the late Silurian. It represented the condensed vestiges of an internal ocean, gradually evaporating amid evolving worldwide dynamics. Comparable accumulations arose in troughs from West Virginia to Ontario, forming a vast ancient salt layer harvested by miners eons afterward. Such evaporate formations reveal key insights into the late Silurian climate. Only in comparatively dry settings does evaporation outpace rainfall, with solar heat drawing moisture from a depression quicker than streams or showers could replenish it. The buildup of extensive evaporate layers indicates that accumulation zones endured extended dry spells, possibly recurring seasonal scarcities or enduring drifts to aridity. Yet this didn't imply a global desiccation. Weather patterns vary by locale, so factors fostering evaporates in one trough could spare distant biomes thousands of kilometers off. Still, it hints that the humid, temperate, reef-nurturing climate dominating much of the Silurian, was yielding to greater fluctuations. The Caledonian Range, freshly elevated and lofty from the tectonic clashes forging La Russia, underwent swift erosion then. Streams bloated with debris cascaded from its slopes, transporting sand, pebbles, and silt to lingering coastal flats and nearshore waters. This material settled into hefty beds of reddish and tan sandstone, the Old Red Sandstone, which lent the supercontinent one of its monikers. Its hue stemmed from iron oxide, basically rust, signaling deposition in oxygenated land settings far removed from the oxygen-poor depressions yielding the dark shales of early Silurian times. Imagine positioning yourself along the late Silurian shores of La Russia, gazing toward the interior highlands. You'd witness a landscape mid-transformation. Horizon-dominating summits remained striking, yet diminished from their height, mere millions of years prior, sculpted by ceaseless ice and precipitation. Streams approaching bore heavy, ruddy loads, fanning them over alluvial expanses where pioneering vascular flora started rooting beyond mere seaside marshes. Atmosphere was inhalable, the protective ozone intact, rendering once lethal UV rays a tolerable risk instead of a total block to land-based organisms. Oceanic realms evolved as well, albeit with subtler alterations than terrestrial upheavals. Mid-Silurian mega-reefs persisted in operation, though their makeup altered as certain clades waned and successors ascended. The late Silurian saw multiple small-scale die-offs, short bursts of heightened loss that trimmed select branches while sparing the rest. Though none rivaled the Ordovician-ending catastrophe in scale, cumulatively, they drove a steady reshuffling of sea life, set to intensify come early Devonian. Amid it all, fishes proliferated with little hindrance from perturbations troubling certain invertebrates. Jawhead varieties grew prevalent, their offspring venturing into novel niches and testing innovative forms. Placoderms were proliferating, their plated bodies increasing in size and variety over successive millions of years. Acanthodians navigated seas and rivers alike, featuring thorny fins and prominent eyes that lent them a somewhat contemporary look. Conditions were ripening for the Devonian era, destined to earn the title of the fish-dominated age, when jawhead vertebrates would at last secure the supremacy that had dogged them during the Silurian. Meanwhile, on terra firma, the foothold claimed by Cooksonia and initial arthropods was building speed. Vegetation was pushing farther from its starting points along marshy shorelines, tracing waterways deeper into the landmasses. These early flora remained modest in stature, uncomplicated in form, and restricted to damp locales where the absence of proper roots posed no deadly drawback. Yet they persisted and evolved, fostering habitats that grew ever more intricate across epochs. As the Silurian drew to a close, the land masses shed their utter desolation. Fringes of green now hinted at vitality, a stark contrast to the lifeless state of merely 20 million years prior, spanning roughly 24 million years. The Silurian was a compact interval by geological reckoning, shorter than many eras, yet ample for sweeping shifts to take hold. The planet, rising from the Ordovician extinction, was depleted and shaken, its biological networks stripped down by disaster, with remnants laboring to recover from the planet's penultimate great die-off. In contrast, the realm transitioning into the Devonian brimmed with abundance, intricacy, and deep-seated alterations from breakthroughs that would resonate across the Phanerozoic's ensuing 400 million years. What legacies did the Silurian leave? How had the world shifted from this era's dawn to its dusk? Such inquiries guide us toward wrapping up our exploration of this pivotal slice of planetary past. Geologically speaking, 24 million years flies by quickly. Its predecessor endured 45 million, while the succeeding Devonian would stretch over 60 million. Even the concise Cambrian extended 53 million before yielding to what followed. Judged thus, the Silurian emerges as a fleeting bridge linking the ruin that closed one epoch to the burst of variety that ignited the next. Still, within that brief window, it drove changes so foundational that their imprints linger in our surroundings now. Reflect on the jaw, with each bite, utterance, grin, grimace, or stretch of the mouth. You're employing a feature that debuted in Silurian waters, those gill supports curving inward to form the earliest basic jaw, triggered a chain of evolution, yielding all present-day jawed vertebrates. That encompasses over 60,000 species of fish, amphibians, reptiles, birds, and mammals, including the one absorbing this narrative. In scientific parlance, the shift sounds routine, merely adapting bone parts from one role to another. But its ripple effects were profound. Jaws enabled aggressive hunting, accurate food handling, dentition tailored to varied menus, and ultimately, the nuanced sounds enabling human language. Absent the Silurian's piscine advances, your visage would differ utterly. Ponder the terrestrial realm, too. Pre-Silurian continents lay barren for some 4 billion years, battered by UV rays and hosting little beyond bacterial films. By the Silurian's close, vascular plants had taken root in seaside bogs, their stalks reaching upward, spores carried by breezes. Arthropods trailed in their wake, respiring via spiracles, foraging and preying amid nascent dirt born of stone erosion and decaying organics. These trailblazers were tiny and tied to humidity, far from the woodlands and meadows to come. Nonetheless, they breached an irreversible barrier. Life, once ashore, would never fully withdraw to oceanic origins. Finally, weigh the ozone shield. The air's composition, pivotal for landward expansion, hit a vital tipping point in the Silurian, as oxygen climbed sufficiently to form a robust barrier against solar harm's worst. This unseen shift, imperceptible to contemporaries, stands as perhaps the era's paramount evolution. Without a protective ozone layer, land plants couldn't take root, terrestrial arthropods wouldn't have emerged, amphibians wouldn't have ventured onto Devonian mudflats, and dinosaurs, mammals, or humans reflecting on ancient history would never have arisen. The Silurian atmosphere paved the way for today's world in ways that are nearly impossible to exaggerate. Think about the reefs, the stromatoporoid coral reef complexes that thrived during the Silurian, marked a dramatic increase in the intricacy of ocean ecosystems. These towering multidimensional formations provided homes for countless species, fostering biodiversity that extended well beyond their own structures. Far from simple gatherings of nearby creatures, these reefs formed interconnected societies, full ecosystems featuring intricate food chains, mutualistic partnerships, and regulatory cycles that sustained balance across vast stretches of time. The reef-building patterns that took shape in the Silurian persisted into the Devonian, and further, ultimately leading to the coral reef environments that today rank among Earth's richest in biological variety. Now consider the land masses. The tectonic clash that created Laurussia and the Silurian played a pivotal role in assembling Pangaea, the supercontinent that would shape global landscapes for the following 200 million years. The Caledonian Range, born from that impact, weathered down to form the deposits holding the fossils we examine now. Meanwhile, the seam linking Scotland and England would one day be traversed by people oblivious to crossing what had once been an oceanic frontier. The Silurians' shifts in geography laid out blueprints that would steer weather patterns, sea currents, and life spread for hundreds of millions of years ahead. These influences aren't mere trivia for geologists delving into antiquity. They form tangible threads in the tapestry of our current reality, both visible and subtle. The oil fueling our vehicles and factories sprang from Silurian black shales. The limestone constructing our buildings and lining our highways often derives from Silurian reef life. The salt, safeguarding our meals and clearing winter streets, came from Silurian seas that dried up. Even your own form, with its hinged jaws, oxygen-processing lungs, and backbone, bears the legacy of breakthroughs first seen in fish, gliding through long-gone waters, 400 million years back. Encountering your Silurian forebears, those early diversifying jawed fishes or the small arthropods newly venturing ashore, you'd hardly see family ties. They'd appear completely foreign, beings from an era so remote that shared traits seem inconceivable. Yet the bond endures, encoded in your genes, shaped into your build, and evident in each inhalation or utterance. You embody a Silurian legacy, distanced from those trailblazers by 400 million years of adaptation, yet tied to them via a continuous lineage reaching back to those balmy, shallow waters where your core traits first evolved. The Silurian bestowed jaws upon us. It opened up the land. It crafted the air shield enabling life on solid ground and the reefs buttressing ocean diversity. It sculpted the land arrangements, guiding evolutionary paths for ages to follow. Spanning just 24 million years, a fleeting interval in life's 4 billion-year saga on our planet, this serene epoch drove shifts whose reverberations would resonate through every later era. And with that, our tale nears its close, at least for the Silurian segment. The waters are pulling back, the peaks are crumbling, the planet is evolving in directions that will soon push it past this era's limits. But before consigning the Silurian to geology's records, let's revisit that primordial realm one last time. To linger on its coastlines and gaze at the sun dipping below vanished horizons. To bid farewell to an epoch that contributed so profoundly to our essence. 444 million years ago, the seas fell silent. We started this exploration amid disaster's wake, poised by a desolate shoreline, observing waves washing over shelves denuded of nearly all life. The Ordovician Silurian extinction had wiped out 85% of sea species, dismantling food networks honed over hundreds of millions of years. The remnants clustered in safe havens, their numbers dwindled to faint echoes of former abundance, their prospects dim in a seemingly hostile environment. Had you stood there, seeing pristine waves kiss empty stones, you might have questioned if life could rebound from such devastation, if those oceans would stay barren eternally. The oceans did not stay barren. In just a few million years, those that endured started to multiply, their offspring occupying the empty spaces and piecing together the shattered web of life that disaster had torn apart. This rebound went beyond simply replacing what vanished. It reshaped the very essence of ocean existence, not envisioning new possibilities for sea dwellers. Local species from the Ordovician era yielded to widespread groups that connected far-flung regions worldwide. Simple reefs from prior times gave way to massive formations of strumata, poroid, and coral, vast living edifices extending hundreds of kilometers alongside continental edges. The tough, jawless fish that once foraged along the bottom now shared space with innovative types, boasting pivotal jaws and seizing fangs. Hunters capable of chomping and ripping unlike anything before. Then, the shores beckoned. For 4 billion years, land masses had lain dormant, their barren expanses scorched by rays, their stones untouched by root systems, their quiet pierced only by microbes. The Silurian altered everything, with the ozone shield firming up. An unseen barrier finally rendered the surface habitable after eons of hostility. Delicate greenery edged from the shallows, their plumbing tissues ferrying water to upright stalks reaching for light. Jointed bugs trailed behind, inhaling through breathing holes, imprinting trails in mud that hardened into rock. As the era closed, land borders bloomed with hints of green, outlining the forebears of all future, woodlands, fields, and prairies. The planet that exited the Silurian bore little resemblance to the one that had entered. Land masses had smashed together, thrusting up peaks whose worn bases we tread even now. Jawed swimmers sparked a lineage of changes leading to every faced backboned animal, from sharks and salmon to frogs and lizards, sparrows and elephants, and all humans who ever walked. Ocean habitats got a total overhaul from the ground up, forging reef patterns and group dynamics that endured for hundreds of millions of years. And existence claimed its initial lasting perch on terra firma. A toehold that swelled to blanket continents in teeming varieties, beyond the dreams of those early trailblazers. 24 million years, a mere flicker in the grand timeline of a 4-billion-year-old world, poised for billions more. Yet that brief span upended it all. The Silurian lacked flash. It wasn't marked by wholesale die-offs or bursts of wild evolution that seized the spotlight. Instead, it unfolded gently, methodically, through steady rebuilding and thoughtful advances. Still, its achievements underpinned all that came after. You embody the Silurian legacy, the jaw framing your speech, the lungs drawing breath, the vertebrate frame propelling your steps. These all stem from breakthroughs in fish and arthropods treading a realm slowly mending after ruin. Strolling amid trees, you trace the far-off heritage of Cocconia and its relatives, those minuscule flora that showed land could host life. Gazing at dusk over waves, you see rays hitting seas whose frameworks echo Silurian reef setups, enduring designs through 400 million years of flux. The Quran seeks no tribute from us. It doesn't insist on memory or thanks. Beings in those primordial waters couldn't fathom the tomorrow they forged. They knew nothing of how their trials and tweaks would resonate across ages, molding a reality alien to their own. They just endured, one cycle to the next, embodying life's eternal drive. To hold on, evolve, and infuse every slot with boundless inventive flair. Through that, they handed us our current realm. The night deepens, and our voyage stretches far. We've spanned 24 million years of planetary saga, from desolate post-apocalypse waters to verdant continental rims of the late Silurian. We've observed reefs surging from depths and swimmers gaining bites. We've witnessed initial flora staking claims ashore, with pioneer arthropods pursuing gulping atmosphere in a milestone for beasts. We have lingered on coastlines long vanished from the map, gazed at heavens whose very composition has shifted over eons, and pictured ourselves in an era so remote that the land masses themselves have drifted thousands of kilometers from their ancient positions. And now, the moment has arrived to pause. The Silurian oceans lie still this evening. Swells lap against the continental shelf in that unchanging cadence they've held for countless millennia, a pattern they'll sustain for eons yet to come. In the shadowy depths offshore, a stromatoporoid reef builds itself layer by delicate layer, offering its modest addition to a formation that demands ages to reach fruition. Crinoids undulate softly in the mild flow, their plume-like appendages sifting nutrients from the sea. A trilobite burrows into the mud, curling into a defensive sphere as daylight withdraws from the sunlit shallows overhead. Along the shoreline, the earliest vegetation stands motionless, their basic stalks absorbing the final rays of a sun already dipped below the horizon. Amid their roots, a millipede creeps deliberately through the moist debris, propelled by its legion of limbs on a path without a clear end, even to itself. The earth is hushed, the waters are hushed, the planet inhales and exhales with deliberate slowness, the timeless pulse of tides that have surged and receded since well before any life form arose to perceive them. You have ventured deep this night across temporal expanses and vast distances, delving into the profound ledger of a world that has chronicled its history for 4 billion years. The Silurian has unveiled its mysteries to you, its reefs and its fish, its flora and its arthropods, its emerging peaks and its converging seas. These aren't mere relics of bygone eras. They form threads in your personal narrative, episodes in a self-portrait you are unaware of possessing, etched in rock and embedded in the framework of your own form. Allow them to take root now, these primordial recollections, these visions of a profoundly altered realm. Let them sink like silt through calm depths, claiming their spot in the profound recesses of your thoughts, where they may lie in peace. The Silurian is unhurried. It has bided 400 million years to recount its tale. It can afford a brief interlude while you slumber. The waters are balmy and serene. The reefs expand steadily. The initial verdant sprouts stretch toward a firmament that has at last begun to shelter them. In those primordial seas your forebears glide, their minute mouths parting and sealing, their diminutive frames bearing the origins of all that you shall evolve into. They remain oblivious to your existence. They can't envision you, yet they persist in their daily existence. And via them, via the continuous lineage binding their domain to yours, you dwell there as well, poised for emergence. The glow diminishes at last. The Silurian sun dips behind boundless expanses of ocean. The sea shifts from azure to amber to rich indigo. And the earliest stars emerge in a vault that resembles in so many ways the one you recognize. The identical celestial fires gleaming in eternal night. The same primordial radiance touching a sphere that, inch by inch, is shaping into the home you claim. Recline, now. The Odyssey concludes. The Silurian fades into recollection, into fossil, into the profound hush of geological epochs, where everything ultimately resides. Yet its legacies endure, its offerings persist. The jaws, the lungs, the verdant and thriving terrain. These are its bequests to you, transported across 400 million years of transformation, ready whenever you stir. The surges are soothing, the liquid is inviting, the globe is tranquil. Drift off peacefully, offspring of the Silurian. Good night.